my presentation was pose estimation for unknown and uncooperative spacecraft.
1 second. Okay, there we go. Let's start. Sorry. To give a bit of an outline, I'll go over an introduction, and then an estimation pipeline and 2 different measurement models for that estimation pipeline. And then I'll conclude, obviously. In the introduction, I'll go over a motivation, the problem statement, and kind of the goals of this research. The overall motivation for me personally is all about space sustainability and making sure that space is accessible to the future to come. And this image here is showing, all the resident space objects orbiting the Earth right now, and we know this number is bound to increase. Overall, as we think about space sustainability, what I think about is increasing the lifespan of satellites currently in orbit, making them more autonomous, and getting rid of the stuff that doesn't work for us or is broken. In more technical terms, we call that debris removal, in-space assembly manufacturing, and refueling. And all of these share a very common problem that's tough to solve and doesn't happen very often in space, which is that spacecraft touch each other. The main issue here is we don't want to make this problem worse, right? So when we go and deorbit something, the last thing we want is to collide with this thing, and now we have 2 debris. So we need to do this in a way that's safe and autonomous. Right. Yeah. Because of this, my problem statement is derived as follows. We want to perform monocular vision-based pose estimation and shape reconstruction of uncooperative and unknown resident space objects at near true docking range to enable a sustainable space environment. The first portion here is about vision. So we're picking vision sensors because of their low size, weight, power, and cost, which makes it friendly for kind of redundant systems. As Jeff pointed out in his defense as well, this can also just be part of a whole sensor package. So we can think of it as either its own GNC stack or as part of a GNC stack. The shape reconstruction aspect is important when we want to do attitude estimation. It can be really helpful for that. But it's really important when we want to go dock and grasp this thing. If we're trying to dock, it's important to know where the docking port is. And if we're trying to grasp it, it's better to grasp it with the main body than it is, for example, with solar panels. So that's the background there. We care about them being uncooperative because these might be unable to communicate, either because they're broken or because they don't want to, in the case of adversarial scenarios. And finally, we care about unknown resident space objects because of 3 reasons. The first one is kind of similar to the adversarial scenario where we don't have access to the 3D models for whatever reason. The second one is because they don't look like they used to, either because of debris or because maybe the solar panel didn't deploy all the way. Yeah, so that's kind of the summary of my problem statement. The related work is under construction. So this is the literature review, but this is the part that I have done literature reviews, not in slides.
It's the most important part for a good work.
Ah, good to know. I'm gonna keep that in mind. Thank you. The overall goals of this research and how this presentation is framed is with the understanding that we have really good knowledge of the spacecraft dynamics. What we want to do is get measurement models that will work for this problem because we don't really have any. So I'm going to test different measurement models and determine their feasibility for space applications. And the way I'll do that is I'll start from what are we doing on Earth when we have similar problems, and we're going to modify those to fit our applications. So we're going to take a quick aside to talk about how I will be testing these measurement models through the estimation pipeline that I mentioned at the beginning. This estimation pipeline is mostly just a Kalman filter, and so we'll talk about the dynamics and some details there. So why do we need an estimation pipeline at all? Well, because we're getting measurements that are in theory noisy and maybe not super frequent. So an estimation pipeline can help us out with that. Why do we want an unsalted Kalman filter specifically? Because the measurement models are nonlinear. Additionally, the dynamics can be nonlinear, so the position can be linear through an STM, but then the orientation is kind of nonlinear. So we're going to use UKF, and we're going to use the same UKF that now Dr. Jeff Park used on his CNN for a pose estimation paper. So just to give an overview of that UKF setup, we have the state representation here. We're using a multiplicative UKF to handle the constraint on the quaternion. The state is represented through relative orbit elements, the modified Rodriguez parameters, which are estimated using the error quaternion, and the angular velocity. The multiplicative UKF works by maintaining a reference quaternion, and that's how we do the attitude estimation. Yeah. The measurement model, as I mentioned before, is going to change based on what measurement we're using. So I tested 2 different measurements here. The first one is the feature-based pose estimation. So we're going to use off-the-shelf feature detectors and matchers, and we're going to get the pose between images based on those features. The second one is online linked 3D models. So we're going to learn a 3D model of the resident space object and then use that 3D model for pose estimation. Some details to go over before we get into these measurement models. Currently, we assume we know the inertia of the target, that we can map from the attitude of the first image to the principal axes of the target, and that we know the full state knowledge of the surfacer. Some of these are better than others, admittedly. So the last one I think is fine. We can generally assume that our surfacer has pretty good GPS knowledge. The first 2 are mostly just for implementation time. So we can test these measurement models, and if we think they work, we'll test them on more complex scenarios. For testing, I'm using images from the SHIRT dataset, specifically the ROE2 trajectory and the synthetic images that we see on the left in the OpenGL rendering portion there. I'm picking this trajectory because it's more observable of the 2 trajectories that are in the dataset. Cool, so with those details out of the way, we can start talking about the feature-based pose estimation pipeline. The basics of feature-based pose estimation is that we're going to use the difference in locations of features that are matched between images to determine the pose between the images, and then we're going to use this pose as the measurement for a UKF. Note that no 3D model will be learned here, so we're missing our shape reconstruction aspect. We'll get that back at some point. The image below here shows you the ground truth location of hand-selected features on the Tanko spacecraft for the SHIRT dataset. These haven't been matched automatically. We know what the matching is because they're ground truth, to be clear. To give kind of a step back here and look at how this works from the perspective of the UKF, we have the spacecraft and the target at 2 different times here. So on the left is one timestamp, and on the right is another. And we see that both of them are moving in both position and orientation. So our state representation, what it's giving us is those red vectors at each time step, and our measurement is actually going to be the motion of the features in the image plane, which means it'll involve both the motion of the target and the camera. In this case, the camera is attached to the surface, of course. In general, in computer vision applications, we assume that the target is stationary. We just need some math to rule that out, and then refine them. So let's talk about feature extraction and matching. What this is you look at an image in feature extraction, and you select things that are easily identifiable. And then in feature matching, you look at 2 images and you say which points match with the features in another image. For feature extraction, we're going to use superpoint, and for feature matching, we're going to use light blue. These are both neural network-based algorithms, and they work really well across lighting conditions and large baselines. This is important and relevant to space applications, especially the lighting conditions perspective, because we can get very different lighting depending on what time we're taking the image. So we can directly throw these algorithms at SHIRT, and we see that the results, at least from a visual perspective, are really good. There's clearly some noise. It's selecting some features in the background. Maybe I can, like this guy over here. Clearly that's noise. But for the most part, it's selecting features that are good to track. The reason I say this is because it's actually selecting features that we hand selected as the best features to track when we were originally working with the SHIRT dataset. So from here, we have 2 images with some dots on the pictures. How do we get the pose? The classic way in computer vision to do this is you first estimate the essential matrix. This is a matrix that correlates the corresponding points in images. And the most formal definition, I would say, is from this epipolar constraint, which is that first equation there. The f prime and the f here are the normalized coordinates of the features in the 2 images. And what the essential matrix does is, it completes that equation. The second definition is how it relates to our pose, where the square tx is the matrix representation of the cross product. And then R and T are your rotation matrix, and T is your translation. And the third definition is the single value decomposition. In general, if the essential matrix is perfect, as in it perfectly matches those features, you will get that the singular values are 1, 1, 0. As that estimation gets worse, then the singular values detract from that. Note that it's rank 2, and what that becomes is that the translation vector is actually unit norm. So we can't estimate the scale from this process. Once we have the essential matrix, we can estimate the pose in the essential matrix, and you get 4 solutions. And we'll use the chirality condition to select the pose solution. And what this basically is you reconstruct the points using triangulation, and then you make sure that they're in front of the camera. So if they're not in front of the camera, then it's probably not the right pose. We can test this out using OpenCV directly. There's a lot of already implemented algorithms out there. Specifically, OpenCV uses the 5-point solver for the essential matrix, which is an algorithm from 2004 or so. It only uses 5 points, so it uses ransack to determine which of those solutions is best. Here in this image, what I'm showing on the left is the 2D locations of the features that were marked for light blue. So this is the same picture as we looked at 2 slides ago. On the right, what I've done is I've used OpenCV to triangulate the 3D locations based on the pose that OpenCV is telling me should be correct. And so now we have the 3D locations of those features in the first image. We know what the motion of the camera and the target are, so we can apply the ground truth transform to those features and map them to 2D into the second image. What I'm showing here is that those triangulated points are incorrect, right? Because we know what the correct translation is from image 1 to image 2, but the features clearly do not line up. We think this could be because of 2 reasons. The first one is that light blue is very noisy. Even though it looks to be very precise, it could be that it's very noisy. And so OpenCV isn't able to reconstruct the correct essential matrix and therefore pose that will lead us to correct matching. The second potential reason is that OpenCV isn't robust enough. Right? Those are kind of the same sides of the same coin, 2 sides of the same coin, sorry. And so what we're going to investigate is the OpenCV portion of this right now. Mostly because this algorithm is from 2004, and so we want to see if people have done something in 20 years. So let's look at new ways to estimate the essential matrix. Mostly how they do this is by convexifying the problem. They have different ways of solving this problem. Unfortunately, it turns out that this algorithm from 2004 is actually really good. It doesn't have this issue of what's called essential matrix degeneracy. What this is basically, if you try to estimate the essential matrix and all your features are in one plane, like you would in textbooks, you have a scale issue in the essential matrix itself. And so it's no longer rank 2, I think it becomes rank 1, and you kind of have many more solutions than what you would get. In our case, we're working with satellites. They're clearly not flat. But our interpretation is that the features are close enough together and far enough away that when you try to normalize them, it appears to be flat. And so that leads to this essential matrix degeneracy that we get from these more modern approaches. The question here becomes, is it even possible to use light blue to estimate the correct essential matrix? And it's pretty easy to check. We can do an exhaustive search. So what we're going to do is we implemented our own 5-point solver, and we're going to just go through every possible combination of 5 points that light blue give us, and we're going to solve for the essential matrix. We do get the correct pose at some point, and this is an example of 5 points that do get you the correct pose, up to, I think, a couple degrees, which is good enough for us right now. But I don't know of a way to determine that that's the correct one, unless I know what the correct pose is. So we need some sort of metric to determine whether or not we have the correct pose without knowing what it is. The 2 current metrics that I can find and that we have developed, so the current one that there is the epipolar constraint that I talked about before. When we're estimating the essential matrix, what we'll do is we'll sum over all of those features, and then the closest one that gets us to 0 is the one that OpenCV gives you. There's a little bit of details there, but not super important. What we think is happening is that the structure is planar. So what we try to do is let's weigh these different features based on the distance that they have to the features that were used to estimate the essential matrix. Recall that we needed 5 features to estimate the essential matrix, and then we're going to run this epipolar constraint on all the other features. So what we're going to do is we're going to weigh whatever features are furthest away from the features, original features that we used, and we're going to use those to estimate the essential matrix. Unfortunately, that doesn't work either. So right now what I'm doing is I'm searching for a metric that could allow us to select the correct pose. And then what we're going to do is we're going to implement this within a sampling algorithm like RANSAC for computational efficiency. Obviously, in space, we would never want to run through the end computations of this essential matrix solution. It takes minutes on my laptop already, so it's not worth it. So now we can look into online learned 3D models and how those can help us do better pose estimation. So when we talk about online learned 3D models, there's kind of two extreme approaches. The first is full a priori knowledge. You can take this to mean that we already know the 3D model. In this case, what I mean is that we have a data set that's sufficiently large such that whatever spacecraft we're going to get in space is well represented by that data set. The other extreme example is we have no a priori knowledge. We don't know what spacecraft look like. They might look like, a table for all we know. I'm going to claim here that we'll never have enough images or 3D models or CAD models, what have you, of satellites to fully represent the space population. As far as I can tell, Jeff was the first person to come up with a public data set of spacecraft, and there were 57 models. The SHIRT data set, which is of the Tango spacecraft, is not included in that data set, and Tango isn't well represented by this data set. So already we have examples of spacecraft that we know are in space that are not well represented by this data set, and so this claim at least has some ground. So the approach we're going to take is we're going to assume we have no information. We're going to learn fully online. Once these approaches are working, what we're going to do is we're going to apply that knowledge of the fact that we know what satellites look like to get computational gains. In terms of 3D model representations, we have a lot of options. I'm not going to go through all of them, but we're going to try neural network approaches. The reason for this is that they have high rendering power, and so that's going to give us better understanding of the satellite. When we want to go dock or grasp it or what have you, that's going to be pretty helpful. And they lend themselves to mixing both offline and online training, which comes back to that approach of first we're going to try to do this without any knowledge, and then we're going to apply the knowledge that we do have. The most famous of these, I would say, are NeRFs, which are neural radiance fields. The basic idea is that you're going to overfit neural network to store the 3D models. So each neural network set of weights kind of encapsulates a specific scene or a 3D model. They render by ray tracing, which basically means you walk along a ray, and then you sample color and density at different positions along that ray, and then you integrate to get the pixel value. I tested NeRFs on satellites, 3 different implementations that are, I would say, pretty popular. The first one is vanilla NeRF, which you see on the far left. The middle one are planoxels. Planoxels actually don't have any neural representation. They use spherical harmonics and voxels to represent their scenes. And I was really interested in this because of their explainability. The issue, as you can see, is that it doesn't do very well in rendering grayscale images. And I think that's due to the way they're doing the cropping of their voxels. I had issues with other grayscale models for their data set, their algorithm. The one on the furthest right is InstantNGP, which trains the best. But all of these have in common that they're doing okay on reconstruction. They're not doing great. They have poor rendering in the case of planoxels. And there's some hyperparameter tuning and long training times for all of these. A new approach from, I think, last year is 3D Gaussian splatting. So this is kind of akin to triangular rasterization. And the basic idea is that we have a set of 3D Gaussians kind of scattered in the scene with unique color, size, position, and transparency. To render, we're going to project them to 2D, and then we're going to add them up front to back. It works really well. There was no hyperparameter tuning at all, which we really like for autonomous systems in space. It's better reconstruction than we had before. I would say it's too good. And it's faster training. In fact, sometimes I have difficulty knowing which one's which, so the one on the right is the rendered one. You can always tell because it's Gaussian in nature, and so it's more smoothed out than the one on the left, which is the ground truth image. So great, we have this 3D model. What do we do with it? We want to get the pose, right, at the end of the day. So during training, Gaussian splatting, what it does is uses ColMap to get the pose. This is a batch estimator, which doesn't really work well for our sequential application. So we're going to follow the approach from iNeRF. iNeRF uses NeRF as its backbone, as the name implies. We're going to use Gaussian splatting for that. The basic approach is we're going to take a picture and guess a pose. We're going to render the image and compare this rendered image to the image taken. And we're going to perform gradient descent based on the comparison. And you see that working here. The guess pose is kind of when it's looking just back, and the ground truth pose is when it's looking down. So we can see that it works pretty well, at least on this mock model. We can then integrate this into the UKF, the estimation pipeline that I started this whole presentation with, to initialize the backwards Gaussian splatting, if you will. I'm using the a priori mean state estimate in quaternion. And this plot shows you the error in the state estimate for each state. It does really well for quite a while, and then it doesn't. I'm going to say that this is because the 3D model becomes poor, but this is a little bit counter to what I just said about the 3D model being really good. The reason this occurs is because Gaussian splatting has no knowledge of lighting. So when we were training and it saw this face was well lit. But now it's taking an image and it's not well lit anymore. And so what happens is when we do the INF approach, we're comparing pixel to pixel. And so what that means, practically speaking, is those pixels are no longer alike. So it says it can't get the pose. The really neat thing is that, in the previous section, I introduced an algorithm that was really good at dealing with lighting changes, and that's light blue, right? So what we would want to do here is guess the pose, render an image, just as we did with the INF approach. We'll extract and match features, and this is kind of where I get stuck by the previous approach. We want to estimate the essential matrix and the pose in the error, and then we'll map that back to our guess pose to update our pose estimate. And then we'll perform gradient descent as well. The really neat thing about this with respect to the light blue feature matching approach is we only require one image to do pose estimation. But of course, as I mentioned, I'm kind of stopped by the previous section. To give you a teaser, it does work really well. Again, some noise at the top, but that's okay. It again detects kind of corners and lines that are really what we're looking for these algorithms to detect. And it's clearly doing well at these very varied lighting conditions that Gaussian splatting could not overcome. So that's what I'm going towards. But to conclude, what we've talked about today is we've presented measurement models for spacecraft pose estimation, focusing on not utilizing a priori knowledge. The feature-based pose estimation has visually really good matching, so we think it has kind of potential there, but poor pose reconstruction, we think either because the essential matrix estimation techniques are not robust enough, or because the likelihood is failing. 3D Gaussian splatting has great reconstruction and great pose estimation at constant lighting, but this kind of also fails when our lighting is different. The next steps, either in the next couple of months or in the next couple of years, are to improve on the feature-based pose estimation. The first thing we can think of is some new metric implemented with sampling. So what I talked about before is, we had the essential matrix, and the 5-point solver can get you the correct pose. The question is, what metric can give us, can tell us that we have the correct pose? There's also new estimation approaches we could, look into, and training light blue and object-centric scenarios. So light blue is trained on scenes like the Hoover Tower, for example. But we want to train it on more like laptops and desks, so it can learn how those work. Gaussian splatting, we want to actually reduce the fidelity. It works too well, I would say, and so it's too expensive. With respect to other NERF approaches, it's very cheap, but it's still too expensive to run in space, I would say. So we can reduce the fidelity to increase computational efficiency, and we want to mesh that with the feature-based pose estimation to get pose estimation once we have the Gaussian splat. In terms of estimation, we want to look into removing the necessity of a priori knowledge of inertia, which there's literature on this, so we'll look into applying that. And then for computational costs, we're going to look at testing algorithms on flight-like hardware and in closed-loop simulations. I'll put the references next time. But yeah, that concludes the presentation.